Let us discuss about logistic regression. Logistic regression is a supervised machine learning algorithm used for binary classification. So it is similar to linear regression in the sense that we attempt to estimate the model parameters W1, W2, Wn and B during the training stage. And during the testing stage, we use this model parameter to find the output. But the important difference between the linear regression and the logistic regression is that in linear regression we use it for prediction, and whereas in logistic regression we use it for classification. And also the cost function used in linear regression is mean squared error, and the cost function used in logistic regression is cross entropy, which we will see soon. What we have after the dot product between the input and the weights is a pre-activation, which is this term, and this term passes through the activation function f to obtain the predicted output y cap. Our goal during the training stage, as it is a supervised machine learning algorithm, is to minimize the error between the y and y cap such that we obtain the optimal model parameters w1, w2 and so on, wn, and also b. During the testing stage, we will be computing the probability of a particular input belonging to a particular class. So towards the end, for a given test input, we get a particular probability stating a particular input belonging to class 0 or class 1. So our goal is therefore to classify in logistic regression, unlike in linear regression, which was used for prediction. So we use a cost function called as cross entropy, which is shown here, where yi is the actual output and yi cap is the predicted output. We will see the reason why we use this cost function shortly. And we use the activation function called as sigmoid, or the logistic function. We use this because the range of this function lies between 0 and 1, and which is what we needed because we want probability as the output, where the value should lie between 0 and 1, and this function actually has the range from 0 and 1. So our goal in logistic regression is to do binary classification. During the training stage, we try to find the model parameters which minimize this error cost function, and during the testing stage we use these model parameters and the test input and obtain the probability of a particular input belonging to a particular class. So later we use a simple threshold to identify whether it belongs to class 0 or class 1. So there is also a multinomial logistic regression, which we are not discussing here. We are confining this topic to binary logistic regression, where we have only two outputs, class 0 or class 1. Let us discuss the intuition behind using cross entropy as the loss function. Here L denotes the loss between y and y cap, and for a ith example. So as we know, in logistic regression we do binary classification and we expect to have two classes as the output. We noted that using 0 and 1. And for yi is equal to 1, we expect the output for a given input xi as probability of yi is equal to 1, which is notated as yi cap, and for a given input xi, the output of probability of yi is equal to 0 as 1 minus yi cap. So as we know that the output in the logistic regression is the probability of being in one of these either classes. So we need these two probabilities, and our goal is to maximize these probabilities. So firstly we represent these two expressions in one single expression by using this equation. As you can see, when yi is equal to 1, we get yi cap, this term will go off, and when yi is equal to 0, this will become 1 and we are left with 1 minus yi cap. So once we obtain this equation, our goal is to maximize this probability. So when we maximize across all m examples, so we take multiplication of all the probabilities and we try to maximize it. So since logarithm is a monotonic function, we can apply log to this product term, and when we apply logarithmic principles, it becomes summation, and maximizing a function is equal to minimizing the negative of it. So we try to minimize this negative logarithm, and we bring the summation to the outside, and we get this equation 2. Now let us substitute this equation 1 in equation 2. So when you substitute this p of yi given xi here and apply the logarithmic principles, we can get back this power terms to the backside, and we can apply log ab as log a plus b. So we have this term, the power logarithm of a power m is m log a. So we use that principle, and log ab is equal to log a plus log b. So both these formulas are applied here to obtain this final expression. So this is what we want to minimize, and that's what is given here as the loss function. So now let us see how this loss function is used to actually derive the update equations for logistic regression. As we said earlier, during the training stage, our goal is to find the optimal weights which minimizes this loss function. So here we have notated y cap as ai, and then we try to obtain update the weights by using iterative methods like gradient descent. So here this is the update equations for gradient descent. So we need to find out these gradients to obtain these update equations. So our job is to find out dou L by dou Wj and dou L by dou B. So let's start with dou L by dou Wj. So we can use the chain rule. As we know earlier, our inputs get multiplied with weights, and that is equal to zi, and that zi passes through the activation function, and we get ai. So in order to find the partial derivative of dou L by dou Wj, first we need to find out dou L by dou ai and dou ai by dou zi and dou zi by dou Wj. We find out individual terms and obtain the overall partial derivative. The same thing applies to dou L by dou B also. So first let's compute dou L by dou ai. As we know, when you differentiate this whole function with respect to ai, we get yi divided by ai and 1 minus yi divided by 1 minus ai. Since we are differentiating with respect to ai, there is a negative term, so we'll get this minus 1. So when you simplify it, this is what the expression we get, and we know ai is to pass this pre-activation through the activation function sigmoid. So this is what is the expression we have, and when you differentiate dou ai by dou zi, we get ai into 1 minus ai. So in the same way, when you compute, we know zi as the dot product between weights and inputs plus bias. When you compute dou z by dou wj, we get xij. The same way, dou zi by dou b is 1. So now we have these three terms, dou L by dou ai by dou zi, and dou z by dou wj. So when you multiply all these three terms, this denominator and the numerator gets cancelled out, and we are left with ai minus yi into xij. So this is the dou L by dou wj, which we will be using here to update the weights of the model. And for dou z, dou L by dou b, we get ai minus yi. So the final update equations for wj and b are as follows. So these are the old weights, and the new weights are obtained by going towards the negative of the gradient. We have already seen the reason of why we go across the negative of the gradient in the previous video. So in the same way, we apply the update equation for B and obtain the final update equations for weights and biases. So in this way, we use this iterative gradient descent method to update the weights until we reach to a point where the weights have the least error. This is how we compute the weights of the logistic regression. Let us discuss the implementation of logistic regression in Python. So as you can see here, we are importing the NumPy library, and we have a method here to execute the sigmoid activation function 1 by 1 plus e power minus z. And this is the training stage where we pass our input matrix and output and learning rate, which is the eta, and the number of epochs, number of iterations it has to run. And as you can see here, we have weight vectors initialized to zeros, and bias is also initialized to zeros. We could even initialize to some random numbers also, but here we have started with zeros. and we have, this is the stage where we take the dot product between the input and the output. So each of the rows are number of samples, and the columns indicates the uh, input features. So this input, each row is being multiplied with the weight vector, and later we are adding a bias term. So this is the pre-activation, and this pre-activation is passing through an activation function sigmoid and obtain the post activation y hat. So in our theory we have also notated this using AI. So once we obtain both A and Z, we compute the gradients of weight and bias using the expressions which we derived, which is AI minus y or y hat minus y dot product of xij, which was the expression. So we are multiplying with the x term. So and late, and also we have a db, which is y hat minus y or a minus y. So since we are adding for each of these terms, we are dividing by the number of samples here. So once we get the gradients for both weight and the bias, we multiply with the learning rate, and we use this update equation, gradient descent update equation. So w is equal to w minus learning rate into the gradients. So and the same thing goes with the bias, b is equal to b minus learning rate into db. So in this way we update it, and this we try to do it for number of epochs. So each time we pass through each of these examples and try to iterate for number of times, so that the weights get stabilized and reach to a point where we have the minimum error. So these are two functions to predict the probabilities. We know in logistic regression we do binary classifications, and the outputs are the probabilities. So when you pass the trained weights to the new input, we get the probabilities as the output. So and also we can predict this class by using a simple threshold. Once if the output post activation pass crosses a particular threshold, we can classify into one of the classes, either 1 or 0. So this is a test input. We are giving a 5x2 matrix as an input, and we have indicated that first 3 belongs to the class 0 and the second 2 belongs to class 1. So during the training stage we give both input and output, and we expect our model to train the weights, which is to find the weights w and b. And once we obtain the weights, we can use those weights during the testing stage to predict the probabilities for a new test input, and also find out which class it belongs to. So once we trained these inputs and for the corresponding outputs, we got these as the weights, 4.611 and minus 2.06, and bias b as minus 6.67, and so on. So now when you give a test input, something like 1 comma 1.5, we get the class as 0, and we can change this test input and check for different what is the corresponding class it finds out. And these are the probabilities for the all the inputs while we trained. So one test example we can check it. If we replace this with 3, and when you run it, it is indicating that it belongs to class 1. So in this way we can train the logistic regression and also do binary classification for any unknown test input.